GCSE Physics, Paper 1.
Energy. Energy stores and transfers. Energy cannot be created or destroyed, which means it can only be stored or shifted from one place to another. There are 8 energy stores that you must memorize for the exam. Anything that moves holds kinetic energy, while anything lifted high above the ground contains gravitational potential energy. Elastic potential energy is stored inside anything stretched or squashed, like a rubber band. Thermal energy relates directly to heat, meaning the warmer an object gets, the more thermal energy it stores. Chemical energy is locked inside the bonds of food, batteries, and fuels, while nuclear energy is trapped deep inside the nucleus of an atom. Finally, electrostatic energy exists between interacting electrical charges, and magnetic energy behaves similarly between magnets. Energy shifts between these 8 stores in 4 distinct ways. It can move mechanically by a force, electrically by a current, by heating, or by radiation using light or sound waves. When reviewing this, be careful never to say energy is used up or lost. Examiners do not accept that phrasing and will penalise you for it. You should always say energy is wasted or dissipated into the surroundings, usually as useless thermal energy. Kinetic and potential energy calculations. What goes up must come down, and in physics, this means energy stores are constantly trading places. At the top of a roller coaster, there's maximum gravitational potential energy, but as it falls, that store empties and fills the kinetic energy store instead. You need to master 3 core formulas to calculate these changes. First, gravitational energy is calculated by multiplying mass by gravity and height. On Earth, gravity is almost always given as 9.8 newtons per kilogram. Second, kinetic energy equals half times mass times velocity squared. Third, elastic potential energy equals half times the spring constant times the extension squared. The spring constant just tells you how stiff a spring is, while extension is how much longer the spring got, not its total length. The golden rule for these questions is that in a perfect system with no friction, the loss of gravitational potential energy perfectly equals the gain in kinetic energy. If an exam question says a falling object drops and loses 100 joules of gravitational potential energy, you do not need to do any more maths to find the kinetic energy at the bottom because it's exactly 100 joules. Specific heat capacity and required practical 1. Why does a concrete pavement get scorching hot under the sun while a swimming pool stays nice and cool? It's all down to specific heat capacity. This concept is simply a measure of how much energy it takes to heat up 1 kilogram of a material by 1 degree Celsius. Water has a massive specific heat capacity, meaning it absorbs a lot of energy before it warms up, while metals have a low capacity and heat up incredibly fast. The formula states that the change in thermal energy equals mass times specific heat capacity times the temperature change. For the temperature part of the formula, never plug in the starting or ending temperature on their own. You must subtract them to find the difference between them. If water warms up from 20 degrees to 30 degrees, it's the 10 that you use in your formula. To measure specific heat capacity in a school lab, you blast a material with electricity and track how the temperature responds. The setup requires a 1 kilogram block of metal, such as aluminium, which has 2 holes drilled into the top. Inside the first hole, you place an electric immersion heater, and inside the second hole, you place a thermometer. The heater is connected to a power pack and a joule meter, which physically counts the energy entering the block. First, you measure the mass of the block using a digital balance. Second, You wrap the block tightly in an insulator like bubble wrap to stop heat escaping into the air. Third, you place the heater and thermometer into their holes and record the starting temperature. Fourth, you turn on the power supply and start a stopwatch, leaving the experiment running for 10 minutes. Finally, you record the ending temperature and the total joules shown on the joule meter. You then rearrange the formula so specific heat capacity equals energy divided by the mass times the temperature change. Examiners will often ask why your calculated lab value is higher than the official textbook value. The answer is always that thermal energy escaped into the surroundings rather than going into the block. To fix this error, you tell the examiner you'll add more insulation to trap the heat. Work is done whenever a force moves an object or when an electrical current flows through a wire. The formula is straightforward because work done equals force multiplied by distance, where work is measured in joules, force in newtons, and distance in meters. Power measures how fast that work is being done or how fast energy is being transferred. The two formulas state that power equals energy divided by time, or power equals work done divided by time, where power is measured in watts and time is in seconds. Efficiency measures how much useful energy you get out of a machine compared to what you put in. Because energy is always wasted as heat due to friction, no machine is ever 100% efficient. You calculate this by dividing the useful output energy by the total input energy. The exam will often test this using a Sankey diagram, which represents efficiency visually. The total width of the arrow on the far left represents the total input energy. The arrow path that continues straight ahead represents the useful output energy, while the branch that bends sharply downwards represents the wasted energy. Houses reduce energy bills by using loft insulation to trap air, cavity wall insulation to stop air circulating between brick layers, and double glazed windows to create a vacuum gap between two panes of glass. On a larger scale, countries must choose between non-renewable and renewable energy resources to generate electricity. Non-renewable resources like coal, oil, gas, and nuclear fuel will eventually run out because they can't be replenished as fast as they're consumed. They are, however, highly reliable because they burn on demand. But burning fossil fuels releases carbon dioxide, which drives global warming, and sulfur dioxide, which causes acid rain. Renewable resources like wind, solar, and hydroelectric power will never run out. They're clean because they do not emit greenhouse gases during generation, but they are unreliable because if the wind stops blowing or the sun goes down, electricity generation drops to zero. Never write the phrase "it causes pollution" in your exam because you will get 0 marks. You must be specific by stating exactly what gas is released and how it damages the environment. Electricity, circuit symbols, and electrical charge. Electrical current is an invisible traffic jam of tiny particles called electrons flowing through a wire. To map out these circuits, you must recognize universal symbols. A battery is drawn as 2 or more cells connected together, where the long line represents the positive terminal and the short line represents the negative terminal. An ammeter measures current and must always be wired in series within the main loop, while a voltmeter measures potential difference or voltage and must be wired in parallel like a bridge across a component. There are also special resistors like the light-dependent resistor, which is a rectangle inside a circle with arrows pointing at it, and a thermistor, which features a diagonal line with a flat foot cutting through the rectangle. To calculate the movement of these particles, you use the formula where charge flow equals current multiplied by by time. Charge is measured in coulombs, current in amperes, and time in seconds. Current represents the speed of the traffic, while charge is the actual amount of electrical stuff that passed by. Be careful of the time trap in this calculation. Examiners will almost always give you the time in minutes or hours. You must convert it to seconds first by multiplying by 60, or your entire answer will be wrong. Ohm's law. To make electrons move through a wire, you have to give them a physical push, and that push is called potential difference or voltage. However, the wire fights back against this movement, and that restriction is called resistance. You can imagine this like water moving through a garden hose. Turning the tap on high increases the water pressure, which represents voltage, but stepping on the hose squashes the path, which represents resistance. Ohm's law connects these ideas together in the formula where potential difference equals current multiplied by resistance. Resistance is measured in a horseshoe symbol called ohms. If you want more current to flow, you must either increase the voltage or lower the resistance. Students sometimes struggle here because the term potential difference sounds confusing, but it's just a scientific name for voltage, and it represents how much energy is carried by each unit of charge. Practice rearranging this formula into current equals voltage divided by resistance and resistance equals voltage divided by current. The exam will penalise you if you multiply numbers when you are supposed to divide them. And you might also be asked to define an ohmic conductor, which is simply a component like a fixed resistor where the resistance never changes, creating a perfectly straight diagonal line on a graph. Series and parallel circuits. There are only two ways to build an electrical circuit, and you must memorize their rules perfectly. A series circuit contains one single loop. Because there are no branches, the current is exactly the same everywhere in the circuit. However, the voltage from the battery is shared between the components, meaning if you add more light bulbs, they'll all get dimmer. The total resistance in series is found by simply adding the individual resistances together. A parallel circuit contains multiple branches. Here, the current is shared because the electricity splits when it hits a junction. However, the voltage is the same across every single branch, meaning each path gets the full push of the battery. The strangest rule is that adding more resistors in parallel actually lowers the total resistance of the circuit. But this happens because adding branches opens up alternative lanes for the traffic, and that makes it easier for the overall current to flow. Students find this difficult because it feels backwards, so remember to look closely at the circuit diagram first. If a component is on the main loop, apply series rules. But if it's on a side loop, switch to parallel rules. Disconnecting a component in a series circuit breaks the whole loop and stops everything working. But in a parallel circuit, only that specific branch is broken, while the other branches keep running perfectly. IV characteristics and special resistors. Not all components play fair, and many change their resistance depending on the conditions around them. Examiners will often ask you to sketch or identify 3 specific graphs that plot against voltage. A fixed resistor creates a perfectly straight diagonal line through the centre because current is directly proportional to voltage. A filament light bulb creates an S-shaped curve because as more current flows, the metal wire gets hot, causing the atoms to vibrate and increase the resistance, which levels off the graph at the top and bottom. A diode shows a flat line on the left and shoots straight up on the right because it only allows current to flow in one single direction due to a massive resistance in reverse. You also need to know two special sensor resistors using simple acronyms. For a light-dependent resistor, remember the word LERD, which stands for light up, resistance down. For a thermistor, remember the word TURD, which stands for temperature up, resistance down. These graphs and sensors link directly to your required practicals. To change the voltage and get different readings in the lab, you must use a variable resistor in your circuit to alter the flow manually. Mains electricity, wiring and safety. The electricity from a small battery flows in one direction only, which is called direct current. However, the electricity coming out of your kitchen plug sockets constantly switches direction back and forth, which is called alternating current. You must memorise the UK mains values, which sit at a frequency of 50 Hz and a potential difference of 230 volts. Inside a standard plug, there are three colour-coded copper wires. The live wire is brown and carries the dangerous 230 volts into the appliance. The neutral wire is blue, and it sits at 0 volts and completes the circuit by carrying current away. The earth wire has green and yellow stripes, and it sits at 0 volts and is a safety wire that only carries a current if a fault occurs. If a live wire snaps inside a metal toaster and touches the casing, anyone touching the toaster will get a fatal shock. Because the metal casing is wired to the earth wire, the electricity surges down to the earth wire instead. This sudden massive surge of current instantly melts the thin wire inside the fuse, and this breaks the circuit and isolates the power safely. To remember the positions of the wires inside the plug, use the letters of the colours. Blue goes to the left, brown goes to the right, green and yellow stripes go to the top. If an appliance has a plastic case, it is double insulated and does not need an earth wire because plastic cannot conduct electricity to give you a shock. Power equations and the national grid. While your basic circuit formulas track the internal traffic of electrons, the electrical power formulas track the actual output of an appliance. Power measures how fast the machine converts electrical energy into useful work or heat. You have two formulas to calculate this value in watts. First, power equals current multiplied by voltage. Second, power equals current squared multiplied by resistance. Just like the kinetic energy formula, you must square the current first before multiplying it by the resistance. If the current doubles, the power loss increases by 4 times. Once electricity leaves a power station, it travels across the country through a network of cables and transformers called the national grid. Transmission wires have resistance, which means sending current over long distances wastes massive amounts of energy as heat. To fix this, a step-up transformer boosts the potential difference really high before the electricity enters the long-distance cables. Because the voltage goes up, the current drops drastically, keeping the wires cool and saving energy. Right outside your city, a step-down transformer reduces the voltage back down to a safe 230 volts before it enters your home plugs. When writing about this, never say transformers change the power or the electricity. You must state clearly that they change the potential difference and the current. Particle model of matter. Density. Density is simply a measure of how tightly packed the particles are inside a substance. The formula states that density equals mass divided by volume, and it's usually measured in kilograms per meter cubed. You need to know how to compare the 3 states of matter. Solids are highly dense because the particles are tightly packed in a fixed, regular pattern. Liquids have a medium to high density because the particles are still close together but can slide past one another. Gases have an incredibly low density because the particles are far apart and with massive gaps between them. You're guaranteed an exam question on how to measure density in a lab. For a regular wooden cube, you find the mass on a balance, measure the sides with a ruler to calculate the volume, and divide mass by volume. For an irregular object like a bumpy stone, you use a special container called a Eureka can. You fill the can with water until it's level with the bottom of the spout and place an empty measuring cylinder underneath it. When you gently drop the stone into the water, it displaces some water. The volume of the water that overflows into the cylinder is exactly equal to the volume of the stone. You then divide the stone's mass by this overflow volume to find the density. To avoid errors, always read the volume from the bottom of the curved water surface at eye level. Internal energy and latent heat. Every object stores internal energy, which is the sum of the kinetic and potential energy of its particles. Kinetic energy tracks how fast the particles vibrate, which we measure as temperature, while potential energy tracks how far apart the particles are. When you heat a substance, you increase its internal energy, which either raises its temperature or changes its state, but it never does both at the same time. On a heating graph, the sloped lines show the substance warming up because the kinetic energy is rising. The flat lines show a change of state, like ice melting or water boiling, where the temperature stays exactly the same because the energy is being used to break bonds. This raises the potential energy instead. Specific heat capacity deals with temperature changes, but specific latent heat is the energy needed to change the state of 1 kilogram of a substance without changing its temperature. The formula states that energy equals mass multiplied by specific latent heat. Latent heat of fusion applies to melting or freezing, while latent heat of vaporization applies to boiling or condensing. Gas pressure. Gas pressure is caused by a microscopic game of dodgeball played inside a container. When gas particles move around rapidly, they collide with the walls, exerting a tiny force at a perfect right angle to the surface. If you heat a gas up, you increase the average kinetic energy of the particles, causing them to move much faster. Because they're moving faster, they hit the walls of the container much more frequently and with greater physical force, causing the internal pressure to spike. When writing about gas pressure, avoid vague phrases like the particles bounce around more. You must write the exact keywords, stating that the particles collide with the walls more frequently and with greater force. Atomic structure and radioactivity. The history of the atom. Our model of the atom changed completely over time due to experimental discoveries. Originally, John Dalton thought atoms were just solid, unbreakable spheres. Later, J.J. Thomson discovered the electron and created the plum pudding model, picturing the atom as a solid ball of positive charge with tiny negative electrons stuck inside like fruit in a pudding. This model was completely destroyed by Ernest Rutherford during the alpha scattering experiment. Rutherford fired positively charged alpha particles at a really thin sheet of gold foil. He expected them to pass straight through. Instead, 3 things happened, and each gave us a massive clue. First, most particles went straight through, proving the atom is mostly empty space. Second, some alpha particles were deflected off course, because like charges repel, and this proved that there must be a positive charge inside the atom. Third, a tiny fraction of particles actually bounce straight back, and this proved that almost all the mass of the atom is concentrated in a dense central nucleus. Later, Niels Bohr upgraded the nuclear model by proving electrons orbit at specific distances called energy levels. and James Chadwick discovered the neutron inside the nucleus. Radioactive decay. An isotope is simply an atom of the same element with the same number of protons, but a different number of neutrons. When an isotope decays, it emits one of three types of radiation. Alpha radiation is a helium nucleus made of 2 protons and 2 neutrons. It's big and heavy, and this gives it a high ionizing power to damage cells, but a low penetrating power, meaning it can be stopped by a single sheet of paper. Beta radiation is a fast-moving electron ejected when a neutron inside the nucleus transforms into a proton and an electron. It has medium properties and is stopped by aluminium. Gamma radiation is a pure electromagnetic wave of energy. It has low ionizing power, but incredible penetrating power, and it requires thick lead or concrete to stop it. The exam will ask you to complete nuclear equations where the top and bottom numbers must balance across the row. During alpha decay, the top mass number drops by 4 and the bottom atomic number drops by 2. During beta decay, the top number stays exactly the same, but the bottom number goes up by 1 because you gained a proton. Gamma decay changes absolutely nothing at all. Half-life, irradiation, and contamination. You can never predict when an individual radioactive atom will decay, but you can predict exactly how long it takes for a massive crowd of them to halve. This time is called the half-life. To read a half-life graph, look at the starting activity on the vertical axis. Divide it by 2, move horizontally across the curved line, and look straight down to the time axis. Examiners will heavily test your ability to distinguish between irradiation and contamination. Irradiation occurs when an object is exposed to radiation beams from an outside source. The rays pass through the object, but the object never becomes radioactive itself, just like stepping into the sun does not make you emit sunlight. Contamination occurs when radioactive atoms physically get onto your clothes or inside your body. The source is now stuck to you, meaning you are radioactive and will continue to emit radiation until the atoms decay or are washed off. Combined Science Higher Tier. This is your standalone for Combined Higher Tier. It builds directly on top of the foundation. Energy. For those taking the higher tier paper, examiners will rigorously test your calculator skills using the squared symbols in the kinetic and elastic potential energy equations. If a moving object doubles its speed, its kinetic energy quadruples because 2 squared equals 4. You must square the velocity first before multiplying any other part of the formula. Higher tier papers also require you to create a mathematical link between potential energy and thermal energy. You might be asked to calculate the temperature increase of a heavy object when it falls from a specific height and crashes into the ground. To solve this, you first use the gravitational potential energy formula to find the starting energy. Because energy is conserved, all that gravitational energy converts directly into thermal energy upon impact. You must take that exact final number and use it as the energy value in your specific heat capacity formula to calculate the final temperature rise. Electricity. There are advanced resistor rules and alternate power formulas. The most challenging aspect of parallel circuits on a higher paper is the concept of total resistance. You must remember that adding more resistors in parallel actually lowers the total resistance of the whole circuit. This happens because adding alternative pathways is like opening up extra lanes on a busy motorway, making it easier for the overall electric current to pass through. The particle model, mechanical work done on a gas. On a higher tier paper, you must understand the relationship between mechanical work and the thermal properties of a gas. If you trap a gas inside a sealed container, such as a bicycle pump, and physically force the piston down, you're applying a force over a distance against the gas pressure. By definition, this means you are doing mechanical work on the gas. Because work done is equal to energy transferred, this action forces energy directly into the gas particles. This increases the internal kinetic energy store of the gas molecules, and because the temperature of a gas is directly linked to the speed and kinetic energy of its particles, doing work on a gas causes its temperature to rise automatically without using an external heater. Radioactivity, calculating net decline ratios. Higher tier examiners will often avoid simple graph work and instead force you to calculate the net decline of radioactive activity using fractions and ratios. Every single half-life that passes drops the remaining radioactivity exactly by half. After one half-life, the activity falls to a fraction of a half, creating a net decline ratio of 1 to 2. After 2 half-lives, the activity halves again to a quarter, creating a net decline ratio of 1 to 4. After 3 half-lives, it halves once more to an eighth, making the net decline ratio 1 to 8. You must read the wording of these questions with absolute precision under exam questions. If the question asks what fraction of the sample remains radioactive after 3 half-lives, the answer is 1/8. However, if it asks what fraction has actively decayed, you must subtract that from the total, making the correct answer 7/8.